Hi everyone! In this video, we're going to be going over question 10 of the Spring 2021 Data 100 final. Let us say that we have some model y of 1 is equal to theta of 1 times x, and notice that there's no intercept term, where theta of 1 is a real number, and we have x and yi, which are vectors, which takes in n data points with the same common y value c. In other words, the model is fitted to the data points x1c, x2c, and so on to xn of c. Let us also say that we have some model y2, where we have the same thing as the first model, but this time theta 1 is just replaced with theta 2, and it takes in the same x values of the n data points, except with the common y value c prime. So in other words, the model is fitted to the data points x1 c prime, x2 c prime, and so on to xn of c prime. For part A, if we run ordinary least squares on our data, what will be the value of theta 1? Okay, so to find the value of theta 1, we can just do what we normally do to find the optimal value of theta, which is take the derivative of our loss function and set it equal to 0 so we can solve for theta. And we know with ordinary least squares, we're going to be using mean squared error. And our model in this case with theta 1 is just yi is equal to theta 1 times xi. So if we plug this into our mean squared error equation, we'll get 1 over n times the summation of 1 to n of yi minus our model, which is theta 1 xi squared, because we're doing mean squared error, and we take the derivatives of this whole thing with respect to theta 1 and set it equal to 0. So to take the derivative, I'm going to move the derivative to the inside, and we're just going to take the derivative of this whole expression. So using the chain rule, we take the 2 down, and then we multiply by whatever's inside the parentheses, and then we multiply that by the derivative of whatever's inside the parentheses with respect to theta 1. In this case, that's just negative xi. So I'm going to pull out both this 2 and this negative. So we're going to get negative 2 over n times the summation of I is equal to 1 to n of yi minus theta 1 xi times xi. Okay, and I'll move the work to up here. So I'm going to just divide both sides by negative 2 over n. Negative 2 over n is a constant. If we divide 0 by a constant negative 2 over n, or if we divide 0 by anything, that's still just 0. So we can just get rid of the negative 2 over n. And then I'm going to multiply these two expressions out. So now I'll get the summation of I is equal to 1 to n of yi xi minus theta 1 xi squared. And again, we divided both sides by negative 2 over n, so we don't have the negative 2 over n anymore. So now I'm going to split this into two summations, yi xi minus summation of theta 1 xi squared. And we're doing that because we want to get the theta by itself on one side of the equation so we can solve for what the optimal theta 1 should be. So now I'm going to move the second expression to the right hand side. I'm just going to add it. So now it's just equal to the summation I is equal to 1 to n of theta 1 xi squared. And I can just take the theta out of the summation because it's a constant. So I get the summation of I is equal to 1 to n of yi xi, which is equal to theta 1 summation of 1 to n xi squared. And now if I divide the left hand side of the equation by this summation, I'll get summation of I is equal to 1 to n yi xi over the summation of 1 to n of xi squared. Okay, so normally this is where we stop with our expression and solving for theta. But in this case, we have an additional piece of information that we know, which is that our yi's in this case are always c, because it says that we take an n data points with the same common y value c. So all the y values are the same. So I can just plug that into this equation. So my yi is now just c, and because c is a constant, we can just take it out of the summation. So c will just move to the front, and then we're left with the rest of our expression. So this would be our theta 1. And we can see that this matches with option 3, which is this one here. Moving on to part B, we now choose to combine all of our data points and fit to a combined model. So y combination is equal to theta combination times x of combination, where we have theta combination and x combination and y combination. In other words, the model is fitted to the data points x1 of c to xn of c with x1 of c prime and xn of c prime and are fed into y combination. Which of the following is the relationship between theta combination, theta 1, and theta 2? Okay, so for this question, it's important to realize that our new x combination is just equal to 2 times our original x, because we are just using the same data points that we have from both models, and we know that both models have the same x data points. We use x1 in both models, we use x2 in both models, all the way to xn and xn. Only the y is changing, because in the first model our y is c, and in our second model the y is c prime, but the x's still remain the same. So we're basically just including the same x values twice, which is why x combination is equal to 2 times x, which is our original x values. Okay, and then something else to realize is that we just calculated that theta 1 is equal to c times summation of I is equal to 1 to n of xi over summation I is equal to 1 to n of xi squared. And from this, we already know what theta 2 is, because theta 2 is also fitted to the same exact model. Yi is equal to theta 2 xi, just instead of this being theta 1, it's theta 2. So in that theta 2 is just going to be c prime times summation of I is equal to 1 to n of xi over summation of I is equal to 1 to n of xi squared. Okay, and this is going to be important later for us to find the correct solution. So in order to basically find what theta of combination is, we can do the same thing that we used to solve for theta 1 and theta 2, which is taking the derivative of our loss function and setting it equal to 0. So our loss function in this case, again, we're using mean squared error. So we're going to get 1 over 2n this time, because instead of having just n points, we have 2 to the n points because we're including our x values twice. So this is 1 over 2n times the summation of I is equal to 1 to 2n of yi minus theta combination, I'll just write that as theta of c, times xi squared. And again, we're going to take the derivative of this entire thing and set it equal to 0. So same as before, we're going to take the derivative of whatever's inside the summation. So this becomes 2 times yi minus theta c xi times the negative xi. I'm going to pull out the 2 and the negative, so we get negative 2 over 2n, summation I is equal to 1 to 2n of yi minus theta c xi times xi is equal to 1. Divide both sides by negative 2 over 2n, and that'll just cancel it out. So now we're just left with summation of I is equal to 1 to 2n, and I'm going to split up our summation into two different summations. So the first summation is going to be yi xi, and then minus summation of I is equal to 1 to 2n of theta c xi squared. And moving this expression to the right side, summation of I is equal to 1 to 2n, yi xi is equal to the summation of I is equal to 1 to 2n theta c xi squared. We can just pull the theta c out because it's a constant, so theta c is equal to summation of I is equal to 1 to 2n of yi xi over the summation of I is equal to 1 to 2n of xi squared. Okay, so now what we can do is actually split apart this top summation, because this summation is equal to just summation of I is equal to 1 to n of yi xi plus summation of I is equal to 1 to n of yi xi. So we have it twice, and then the bottom still remains the same. And we know that because we added together our two models, we have the points from the first model, which is x1c, all the way to xn of c, and then the points from the second model, which is x1c prime, all the way to xnc prime. We know that one of these, the yi's would just be c, and the other one, the yi will be c prime. So I'll move this to up here. But this is just the same thing as summation of I is equal to 1 to n of c xi for the first model, and the summation of I is equal to 1 to n of c prime xi. And in this bottom here, we can actually split apart, or not split apart the summation, but we can rewrite it so that it just becomes 2 times summation of I is equal to 1 to n of xi squared. because this is the same thing as summation of I is equal to 1 to 2n, but now we're just taking the 2 down. Okay, and again, we can pull out these c's because they're constants. So this is just c summation of I is equal to 1 to n of xi plus c prime summation of I is equal to 1 to n of xi. And then divided by, I'm going to move this 2 to the 1/2 here, and then summation of I is equal to 1 to n of xi squared. Okay, and we can actually simplify this expression further. So I'm going to split apart this entire fraction into two fractions. So this will just be c times summation of I is equal to 1 to n of xi over summation of I is equal to 1 to n of xi squared plus c prime times the summation of I is equal to 1 to n of xi over summation of I is equal to 1 to n of xi squared. Okay, and we wrote down what these two expressions were beforehand. This is just equal to theta 1 and theta 2. So subbing this whole thing in, this is just equal to 1/2 times theta 1 plus theta 2, which is equal to theta 1 plus theta 2 over 2. And this is just equal to this first option here, option A. Okay, and this concludes the walkthrough video for question 10.